of a vast idea, the one behind the calm pulse of climate models and the quiet work of their grids. We will let the bustling world recede into a gentle, distant hush and lean into the soft glow of understanding. If this gentle space helps you exhale and settle, remember to like and subscribe so more calm journeys can find you whenever you need them. And if you want the learning to keep flowing while you drift, there is a playlist link in the description waiting for you. What city country are you watching from right now? Imagine yourself resting in a dim room, the air still and cool, the soft hum of a fan somewhere out of sight. Your body eases into comfort and your mind begins to float. Before you, in your imagination, a planet turns so slowly that the motion is almost invisible, like a globe wrapped in quiet blue. Around it, delicate lines form, a mesh that hugs continents and oceans like a patchwork quilt sewn by patient hands. Each tiny square or hexagon or softly curved cell is a place where equations breathe in and out. A grid is not loud. It does not shout. It does not rush. It just watches in silence and passes small messages to its neighbors, a whisper from cell to cell, the way dunes share the story of a breeze grain by grain. In that gentle lattice, time advances in small steps. The rhythm is steady, the cadence almost hypnotic. The gentle rhythm continues. In the stillness, you notice how a climate model is like a carefully kept diary of the planet, a way to learn not by peering through a window, but by tracing the shape of the wind, the drift of clouds, the curve of currents. Everything begins with a choice so simple it feels like a lullaby. We cannot solve the entire fabric of the atmosphere and ocean at once, so we take it in gentle pieces. We divide space into cells, like tiles on a calm mosaic. We divide time into steps, like the tick of a quiet metronome. In each cell, at each step, the model keeps track of a few essential things: temperature, humidity, wind, salinity, perhaps cloud droplets and ice crystals, the salt that remembers ancient rivers, the dust that drifts across deserts, the heat rising from warm currents far below. The model moves these without hurry. It nudges, it balances, it checks. The gentle rhythm continues. Imagine the air in a single cell. It has weight and warmth. It has moisture that may rise into a cloud or sink back down as mist. Surrounding it are other cells, each doing its own careful work. Between cells, there are tiny doors called fluxes, where heat and water and momentum pass back and forth. Nothing is sudden, even when the world beyond these lines is full of sudden changes. Inside the grid, everything is a conversation, a step forward in time, and some energy flows in. Another step, and a little water vapor departs. The forces are guided by simple ideas turned into careful mathematics. Warm air rises lightly, cold air sinks with a soft insistence. steps is why climate models take their time. The steps are tiny because the model is cautious. If it steps too far in one go, the conversation becomes confused. If it tries to rush, it misses a whisper and loses balance. A wind that is too fast for the size of a cell can skip across a boundary, like a dancer vaulting over a line instead of stepping to it. To avoid that stumble, the model listens to a quiet rule, a rule about stepping carefully across space and time, a rule that says the message moving through a cell must not outrun the time step. So the model shrinks the step until it is safe, and then shrinks it a little more, just to be sure. This cautious rhythm is gentle on the mind. It is like walking along a shoreline at dusk, heel to toe, unhurried, counting the waves by feel rather than by number. You find yourself softening into this pace. Below the atmosphere, the ocean has its own slow song. The ocean is layered like a vast stack of velvet blankets. Near the surface, ripples and eddies swing softly, and deeper down, the currents move with a patience that resembles the turning of seasons inside a clock. The water remembers. Brine sinks and warm currents rise. Heavy with salt, water slips downward, and fresh water rises with how it was warmed. The steps of the ocean are long and weighty, as if gravity itself were gently tapping the drum. To make the ocean sing with the atmosphere, the model watches both, and it listens to the interface between them, a place of exchange where breezes pick up moisture and warmth, and waves return their coolness like a soft reply. Each layer in the ocean meets a matching layer in the atmosphere, or nearly so, and they trade careful notes. The gentle rhythm continues. Time changes its character. The deeper you go, the surface of the sea responds swiftly to sunlight and storms that swirl the upper waters. But as your mind descends in imagination to the slow rolling thermocline and onward to the abyss, you feel the centuries. Water that sank long ago is still on its path, patient and steady, tracing loops around the globe. That is why climate models keep stepping and stepping. They cannot declare that the story is finished until the ocean has turned its long pages. This is called spin-up, and the word itself feels like a wind-up of a vintage music box. The crank turns, the spring tightens, and the melody finds its tempo gradually, not all at once. The model must run long enough that the deep ocean, with its memories, reaches a calm conversation with the atmosphere above. If it stops too soon, it is like closing a book right when the slowest character begins to speak. So it continues, gently, above the ocean. Sunlight flows in through a filter of gases, and some of that light becomes heat that rises, meets clouds, and scatters back outward into space. In the model, this dance of light is handled with delicate care. The sky is split into layers, each with its own amounts of vapor and tiny particles. Light enters, and the model computes how it should proceed, wavelength by wavelength, band by band, few steps, like a pianist revisiting a tender passage to keep it true. The gentle rhythm continues, and then, when it reaches clouds, the model becomes even more careful. Clouds are fractal quilts, delicate embroidery done by the atmosphere in motions too small for the grid to see. Inside one grid cell, there might be a towering column of vapor, a gentle layer of thin ice, and a drift of raindrops threading downward. The cell cannot see everything, so the model uses soft approximations drawn from measured patterns and thoughtful theory. It lets a fraction of the cell be cloud and a fraction be clear. It guesses how large the droplets might be on average and how likely they are to collide and merge, and it nudges rain into being when the time is right. These choices are watched and tuned, not roughly but with listening. Observations from satellites and aircraft whisper clues, and the model adjusts, like an artist adding a pale wash to the edge of a cloud in a painting. The gentle rhythm continues. Turbulence, too, is a question of scale, not the kind that requires alarm, but the kind that makes the air slightly textured, like silk rippling under your fingers. The grid cannot resolve the smallest eddies, so the model gives the cell a little inner life. It says that within one cell, air swirls in tiny untracked loops, and that those loops mix heat and moisture just a bit. The model adds a gentle smoothing, a careful blending from one edge of the cell to the other. That smoothing is part of why things move slowly. Each step must watch the mixing and then the transport, and then the blending again, as if the cell were a miniature weather system with its own slow breath. Imagine the land beneath all of this, with its varied rug of vegetation. Forests in one place, grasslands in another, soil that dries and moistens, snow that arrives as a quiet blanket, then lingers in shaded folds before receding in the spring light. The land model is not just a passive stage. It breathes water vapor. It holds heat and releases it later, creating small breezes that drift up slopes in the afternoon and down in the evening. The grid over land adjusts not only to the shape of mountains, but to their influence on air. Because the earth is not smooth, and because the model's cells are of a fixed size, mountains become softened. Sharp peaks are rounded just enough that the equations stay kind. Rivers are traced as if with a fine pen, carving invisible pathways that move water from cell to cell, pooling and flowing in a way that matches what we know. The gentle rhythm continues. Sea ice, white and faintly blue, slides back and forth on the ocean like thick paper floating on a pool. It thickens during winter, thins in summer, and sometimes rides currents that nudge it into ridges at the edges, like folds in a blanket. The model lets sea ice stick and slip, a quiet ballet guided by the winds. It decides when the ice in a cell is fractured or continuous, and how much sunlight it reflects. The time scale is slow here too. The ice remembers last winter as well as last night. The model listens for a long time, because that is what this part of the earth requires. The gentle rhythm continues. When scientists want to know how the climate is likely to shape itself over decades, they do not ask the model to tell them a single definite future. Instead, dramatic, but over time they can change the precise arrangement of clouds, the wiggle of a particular jet stream, or the location of a storm. Each ensemble member is a sibling, singing the same melody with a slightly different voice. This is valuable because climate is not the story of a single day, but the average of many days, the distribution of possibilities. The ensemble shows the range of outcomes, a soft fan of possibilities rather than one line. To make that fan, the model must run again and again. The work multiplies gently. The gentle rhythm continues. Alongside these multiple runs, scenarios arrive like slow trains. One scenario assumes we keep the world's energy habits as they are for a while. Another imagines we change those habits. Each scenario leads to new small differences, compounded across time, and each must be explored with care. So the model climbs decades, even centuries. It tallies heat in the upper ocean and then checks the deep ocean. It watches the transfer of carbon between the air and the biosphere and the ocean, a steady exchange that never stops. It keeps track of blooms of tiny algae like a soft green gauze at the ocean surface, and the settling of organic matter into the quiet depths. It follows the gentle chemistry of the air, where ozone and nitrogen and other gases interact slowly, shaping the way sunlight scatters and warms. Every one of these motions takes time. Every one is important to the way the model thinks. The grid itself is a character in this story. Its shape matters. Some climate models lay down boxes like tiles, others spread spheres like beads, and still others use curving unstructured meshes that fit the coastline with loving care. In the ocean, the grid sometimes avoids the pole, where lines would otherwise bunch together. It uses a tripolar design, where the lines swirl around two northern points instead of one. This spreads the cells evenly and keeps the water moving smoothly along the edges of continents. In the atmosphere, the grid might use hexagons or squares, and the winds move across them using careful mathematical rules that maintain balance. The rules are designed to keep mass and energy conserved, because the model knows that a small mismatch, repeated often, can stray into a larger and larger error. The gentle rhythm continues. You can imagine this grid drawn over a globe in a dimly lit room, the edge of the mesh faintly glowing, almost like a lantern shade. On the surface, wind glides cell to cell. In the model, this happens through equations that express Newton's simple idea that acceleration comes from forces, pressure pushing against boundaries, the rotation of the Earth nudging the air to turn. The model takes those equations and writes them in a way that fits the grid, using special stencils and patterns that allow it to pass information from a cell to its neighbors without losing too much detail. Some models use a method that tracks the movement of air parcels along their paths, softly stepping backward to find where each parcel came from before moving forward again. It is like retracing your footsteps in a garden to remember how you got to the quiet bench under the tree. When you ask the model to see more, to resolve clouds more clearly, or to catch smaller eddies in the ocean, performance rises like a tide, and then, because the cells are smaller, the safe step in time becomes smaller as well. To keep that careful rule about not stepping too far too fast, the model must take more steps per day of simulated time. The total work increases gently but inevitably. A day of climate can take many hours of calculation, and a century of climate can take weeks of running on a cluster of machines. This, too, is part of why the models feel as if they stretch on and on, not because they are lost, but because they are listening carefully. Now imagine the computing room where these models run. There is no drama here, only the steady whisper of air conditioning and the patient fans that keep the processors cool. Rows of machines glow with a soft tone, and the floor vibrates very slightly, an almost imperceptible sign of quiet industry. The program divides the grid among these machines, giving a region of the Earth to each. At the edge of those regions, the machines talk to one another to share the values of temperature and wind. This communication is careful and polite. It waits until the neighbor is ready, then hands over the data, then proceeds. The synchrony is part of the dance. One more reason the model cannot rush. If one part moves too quickly, it must pause to let the others catch up. The gentle rhythm continues. Sometimes, to help with this, the model runs the fastest changing parts in small sub-steps. It lets the surface winds move across several tiny steps, while the deep ocean takes a longer step. It balances the short-term flutter of clouds with the slow seasonal drift of ice. This kind of split attention allows the whole to stay stable. It is as though the model has learned to breathe in several rhythms at once. A fast pulse for the places where motion is quick, and a slow heartbeat for the places where motion is deep and cumulative. From the outside, it looks serene. Inside, it is a symphony made of simple repeating notes, carefully tuned. The model's memory is deep, and like all things that remember well, it keeps records. As it runs, it writes down what it has seen, averages of temperatures, counts of storms, measures of energy budgets. It does this gently, not too frequently, so as not to slow itself unnecessarily. Yet the record it creates grows to be large. A long simulation can fill disks with quiet numbers, and to hold them safely, the system checks and saves and checks again. Occasionally, the model pauses to write a snapshot of its entire state, a rest point from which it can start again if needed. This kind of careful saving is another reason the process takes its time, but it is a friendly reason. It is the reason you can wake a model from sleep, gently restore it, and let it continue its walk across time without losing its way. The gentle rhythm continues. Nothing in this model is random chaos. Even where it calls on statistics to represent what the grid cannot see, it does so with a deliberate hand. A parameter governing how sometimes adjusted so that the model, in its calm average, mirrors the Earth we observe. This tuning is not a trick, it is part of the craftsman's work, like setting the tension of a string. The tuned model runs again, and again the grid keeps watch, and the output is compared once more. The seasons align more closely. The energy at the top of the atmosphere balances within a small, acceptable range. The gentle rhythm continues. You can think of the equations themselves as a language of balance. One equation for how heat moves, another for moisture, another for movement, another for mass. They are linked because heat affects motion, motion affects clouds, clouds affect light, light affects heat. The model travels around this loop many times, every step, closing the circle so that nothing is counted twice or missed. When these circles close, the climate that emerges is not forced into being. It is simply allowed to play out in a safe space. It is as if you set a toy boat in a shallow pool and then watch the way it slowly finds its drift. The pool's boundaries keep it safe, and the boat does what boats do, quiet and content. The gentle rhythm continues. Let your thoughts wander now to the concept of equilibrium sensitivity, a measure of how much the planet warms if greenhouse gases rise, and then hold steady long enough for the ocean and atmosphere to breathe together and settle. This is a long-term question. The answer cannot arrive on the first page or even the 10th. The model must wait for the ocean to accept the new patterns of heat, for ice to retreat or return as appropriate, for dust to find its new paths, for clouds to form in new habits. Somewhere far along this run a new balance forms. That balance has a number associated with it, but the number is the least important part. The important part is the patient listening it took to find it. There are moments when practitioners invite adaptive meshes, where the grid refines itself in places of sharp change and relaxes where things are smooth. The idea is lovely, like a camera focusing softly on the subject and relaxing the background. In weather models, this can work well. In climate models, the task is more delicate. The grid must align with the ways multiple subsystems talk to each other. Differences in resolution between atmosphere and ocean can cause discord at the interface if care is not taken. So while some modern climate efforts explore this adaptive idea, many still rely on fixed grids that are simple and harmonious, favoring consistency over abrupt changes. The gentle rhythm continues. Under the grid, in the vertical direction, the design is carefully chosen. Near the ground, a coordinate that follows terrain is helpful because winds that curl around mountain slopes need to see those slopes clearly. Higher up, where the pressure is more important than the ground, a pressure-based coordinate is better. A hybrid system can do both, gradually adjusting from one to the other as you rise. In the ocean, the vertical coordinate can be tied to depth, to pressure, or to density surfaces that tilt gently across basins. The choice helps the model represent the slow tilt of layers, the creeping movement of water masses, and the way traces like carbon and heat are transported. attention to geometry means the numerical steps stay gentle. Where the world shape might otherwise force urgency, the model finds a way to stay patient. The gentle rhythm continues. Even the chemistry of the atmosphere is treated as a series of conversations. Gases react and form others. Some reactions are fast and others are slow, and the model must keep track of them without making a tangle. To do this, it advances chemistry with small steps of its own, nested inside the larger steps of the winds and clouds. Some reactions solve themselves almost instantly during a step, equilibrium reached like water settling in a cup. Others proceed through subtle chains that are computed carefully. The reactions draw energy into the story as well, warming or cooling the air by small amounts that add up across seasons. This integrated approach allows the model to trace not just greenhouse gases, but also the aerosols that scatter light, and the tiny particles that serve as seeds for cloud droplets. The gentle rhythm continues. In the ocean biogeochemistry, the model watches the soft blooming of life. Nutrients rise from the deep and meet sunlight in the surface layer, and phytoplankton take that opportunity with the quiet gusto of spring. They grow, they change the colour of the water in ways so subtle that only a satellite can see the hint of green. Then they sink, soft snow to the deep. The model keeps track, not of every organism, but of a few functional groups that represent this gentle cycle. It notes how these cycles affect carbon, which leaves the surface, and returns, which is stored in shells and dissolved again. The cycles have time scales, measured not only in days, but also in seasons and years. The gentle rhythm continues. There are models that replace the full complexity of the atmosphere with simpler representations. Energy balance models reduce the system to a smooth calculation of input and output, like a dimmer switch for the planet's warmth. They are useful for exploration, for the slow communion of first ideas, but the quiet strength of the large climate models is in their ability to hold many talking parts at once, allowing emergent behavior to come forth like a pattern in a tapestry. That emergence takes time. It requires patience. It rewards patience. Sometimes you may hear of hindcasts, which are runs that cover the recent past to test how well the model can reflect what was observed. In these, the model is nudged with real fields of sea surface temperature, or with estimates of winds and pressure, not to force it to be perfect, but to help it stay near the observed path. If the model, under this gentle guidance, stays close to observations, it is a sign that its inner whispers are well tuned. And then there are projections, which are free runs into the future under assumed scenarios. They are allowed to flow naturally. In these, many small things will differ from what will happen in reality, but the overall distribution, the larger averages, the envelope of humidity and temperature and storminess will resemble the possible world. The gentle rhythm continues. You notice how the model's speed is affected not just by the size of the grid, but also by the complexity of When the system is fully coupled, with atmosphere and ocean and sea ice and land and biosphere speaking to each other at each step, the calculation slows in a meaningful way. This slowing is a sign of respect for the processes being included. It is a sign that the model acknowledges time as a partner rather than an adversary. There is also the matter of chaos, not the kind that brings fear, but the kind that brings sensitivity. If you move a thread by a hair's breadth at the beginning, it may shift the weave later on. This is why climate models are not weather forecasts drawn out for decades. Weather is the tiny detail of the pattern. Climate is the gentle average pattern across the fabric. By relaxing into what can be known, averages, distributions, likelihoods, the model turns what would be a frantic chase into a mindful walk. The gentle rhythm continues. When you imagine the quiet work done on large computers, you can also imagine the quiet work done by the humans beside them. Scientists write code that is meant to be clear and trustworthy. They test small parts with care so that the whole stays true. They compare results from one model to another to ensure that math that holds true in one place holds elsewhere. These comparisons are collaborative and unhurried. Meetings are where notes are compared and gentle questions are asked, not to disrupt, but to clarify. Over time, patterns of agreement emerge, giving confidence. Differences emerge as well, and these are studied with a curious calm. They lead to improvements and better understanding. The gentle rhythm continues. In your mind, you might picture a giant library where each model run becomes a book. Some books are thin, a few years long, exploring one idea. Others are thick, spanning centuries, allowing patterns to show themselves fully. The shelves reach upward into the soft dimness with organized care. On a table nearby, a few books are always open, pages marked with strings. Readers come and go, taking notes in the margins, then closing the covers gently when they are done. The climate model is not a single book, but the library itself, a place where time stretches in a comforting way. Sometimes weather models borrow ideas from climate models, and sometimes climate models borrow from weather models. The two families are related. Weather models run fast and focus on days ahead, often using grid steps that are even smaller, relying on data assimilation to keep their picture aligned with the present. Climate models relax this need to stay in lockstep with observation at every instant, and because of that, they can use simpler, longer steps in some places, but they add complexity in coupling and longer time scales. The exchange between these cousins improves both. Weather models become aware of long-term changes. Climate models inherit techniques that keep their numerical footing firm. The gentle rhythm continues. Imagine yourself walking through soft snow. Every step sinks a little, and then you lift and move forward again. That is how the model moves through time. It presses into a new state, then adjusts and rebalances, then presses again. It checks for stability and accuracy the way you check for footing. If the snow becomes too deep, you shorten your steps. If the surface is firm, you can lengthen. The model keeps a similar sensibility. always ensuring that the story it tells remains believable and calm. In the land model, there is a small, friendly piece that handles the way canopies breathe, leaves open pores and release water vapor, and then close them if the air is too dry or the light is too low. Soil layers beneath hold water in different ways. The top layers give it up easily, while deeper layers hold it like a secret. Snow cover acts as gentle insulation, protecting the ground from the cold and changing the timing of melt and flow into rivers. The model lets river networks weave across cells, following a path that balances realism and computational ease. Water gathered by many cells becomes a stream in the model's quiet arithmetic, and that stream joins others, eventually reaching the ocean in a way that matches the world's gentle geography. Now think of the way storms are represented. In most climate models, storms are not drawn in all their intricacy. Instead, the model gathers their essence. The rising air that forms a storm is allowed to rise in a simplified, softly parameterized way. The result is a world where storms exist as blended patterns rather than as sharply detailed. This is enough to get the climate of storms right. Their frequency, their intensity in an average sense, the way they prefer certain seasons. As models refine their grids, they begin to resolve these storms more directly, which is beautiful but costly, and the time needed grows again. The gentle rhythm continues. If you listen carefully, you notice another whisper in the room where these models run. The power they use. It is not extravagant, but it is meaningful. Computers sip electricity steadily. The cooling systems inhale and exhale, maintaining a safe envelope of temperature. There is a balance here, because using less power and making more efficient code also feels gentle and respectful. So those who build the models often look for ways to rewrite parts, so they run faster without losing clarity. They use new hardware, like graphics processors, to push arithmetic gently forward. But they do this with care, because a change in hardware must not change the essence of the model's voice. Reproducibility is a form of trust. The gentle rhythm continues. To keep trust, models are checked against carefully curated measurements. Satellites see the Earth in broad swaths, measuring light at different wavelengths. Weather stations capture air temperature near the ground, and radio sondes ride balloons upward, tasting the air with sensors as they ascend. Ships and floats measure the ocean's temperature and salinity, leaving behind a trail of tiny numerals that the model can greet and compare itself to. This process is not accusatory. It is a friendly alignment exercise. It helps the model remain a faithful mirror of the world, though never a perfect one, because the world is between one moment and the next, always changing. The gentle rhythm continues. As you drift with this thought, you realize that the model's gentle unfolding in time is part of its value. The slowness is not a flaw, but a feature born from the complexity it honors. In everyday life, slowness can be frustrating, but here, slowness is a sign of care, like the way a gardener waters each plant in turn, or the way a baker rests a dough to let it rise properly. The model could make choices that speed it up, but only by leaving out some of the relationships that make the climate climate system what it is. Instead, it breathes through the steps. Sometimes, when scientists study very long-term questions, like the growth and retreat of great ice sheets, they take a hybrid approach. They let the fast parts of the climate reach a rhythm with a quick run, then press the slow parts forward for a long stretch, then return to the full model again. This alternating, called asynchronous coupling, allows the arc of millennia to be traced without spending a millennium of wall clock time. Even so, the approach is used with care, and the steps are checked again at full resolution so that the story remains consistent. The gentle rhythm continues. By now, you may feel the outline of a vast tapestry. Each thread represents a process: the warmth of sunlight, the curve of a jet stream, the slow drift of a current, the shining of an ice surface, the breath of forests, the small sparkle of sea spray. The grid is the loom. The equations are the motions of the weaver's hands. The model, patient and precise, weaves and reweaves, sometimes stepping back to check the pattern, sometimes leaning in to refine a single line. This is what it means for the model to continue, unhurried, for what feels like an eternity. It is not truly endless. It simply takes the time it needs to make the picture smooth. An ensemble is built, run by run, until there is a gentle fan of possibilities for each scenario. Decision makers do not need a single thread. They need the fabric. They need to know how average temperatures might change to guide designs for gardens and for cities. They need to know how rainfall might shift so that reservoirs can be sized with care. They need to know how sea level might creep upward so that shores can adapt. The model offers this fabric, and it does so quietly, without fanfare, because the math itself is content to be timeless. The gentle rhythm continues. Some parts of the model are called solvers, and they are the inner machinery that moves the equations from one step to the next. There are solvers that treat stiff chemical reactions with special patience, because some reactions transform quickly and some slowly, and the combination can be numerically tricky. There are solvers for radiative transfer that use clever banding methods, grouping wavelengths so that the calculation remains light without losing essence. There are solvers for pressure that enforce balance in winds, making sure that the turning of the earth does not produce spurious features. Each solver is carefully chosen, sometimes compared with others in quiet tests, accepted based on its calm reliability. The gentle rhythm continues. At the edges of the grid, there are boundaries. For the atmosphere, the boundary at the top must be open, because the real atmosphere fades away into space rather than hitting a wall. In the model, this boundary is treated like a soft sponge, absorbing upward moving waves so they do not bounce and create echoes. In the ocean, boundaries at the sea floor and at the coasts are treated carefully as well, ensuring that currents can slide along them without losing their identity. The handling of these edges prevents the formation of artificial reflections that would mar the tranquil progression of time. The gentle rhythm continues. If you close your eyes now, imagine a single grid cell again, with its values stored like tiny beads. represent heat, some represent water vapor, some represent momentum. At each step, the model takes these beads and, using laws that are more like gentle rules than commands, moves them a little to the east, a little upward. Some condense into liquid, some evaporate into gas, some are carried out and replaced by their neighbors. This is the practice, again and again, for every cell. It is small work, but in the largest sense, there is peace in this repetition. Around the midpoint of this unhurried journey, let your shoulders drop and your forehead smooth, and if you feel cozy enough to type slowly and then drift away, we have a quiet prompt for you. How sleepy are you on a scale of 1 to 10? When you are ready, allow your thoughts to wander back to the land of code and grids. The code itself is a poem in a practical language. It has modules for each piece, lines for each calculation, comments that whisper explanations to those who will read it later. It is not a rushed poem. It is a crafted one. The structure is arranged so that pieces can be replaced as understanding deepens, and so that the whole remains comprehensible. Small tests are written that show whether a task, like transporting a tracer across a rotating flow, is done accurately. When these tests pass, there is a quiet comfort in the room, the same comfort you feel when checking a lock and knowing it is secure. The global community of climate modeling is a gentle network of collaborations. Data sets are shared, code is reviewed, experiments are coordinated, so that results can be compared across models. There are initiatives where all models run the same set of scenarios, asking the same kinds of questions and reporting results in the same format. The output is compared, not in a competitive way, but in a collective, harmonizing way. Gradually, the models converge on a common story while retaining their individual voices. Where there are differences, those differences become questions that lead to refined physics, better data, improved methods. The gentle rhythm continues. Consider also the practical side of output. The numbers that represent the future and the past must be shared and read by others, so the model writes them in formats that are clear and documented. Dimensions are labeled, units are carefully noted, a temperature is tagged as being at the surface or at a specific height, so that the meaning is not lost. These careful details are another place where time is invested. They are also places where calm minds take pleasure. There is satisfaction in knowing that someone, somewhere, will open the file and immediately understand what is inside. Within the model runs, there are subtle budget checks. The model sums the amount of water in all its forms across the grid and ensures that it remains consistent. It checks the energy at the top of the atmosphere, just to see how it balances over seasons. If there is a small drift, the modelers find it and correct it with a light touch, avoiding heavy-handed fixes in favor of adjustments that bring the math into better alignment with physical truth. The same is done with carbon, which moves through air and land and ocean in a looping system. These loops are not rigid, they flex with climate. The model follows them with the same steady interest. sense a theme in all of this. The work is quiet, careful, lengthy. It draws from geology, biology, physics, chemistry, mathematics, and computer science. Nothing is rushed because the purpose is not speed, but trust. People will use these results to guide choices that affect communities and ecosystems, and the models are built in a way that respects that gravity while maintaining a soft tone. The gentle rhythm continues. There are seasons when models retire parts of their code. A new method replaces an older one, and the transition is made smoothly. The model runs again, comparing the new with the old to ensure that the essence is preserved. If the change improves the handling of clouds in a region, that improvement is noted calmly. If it slightly slows the calculation, the cost is weighed. Often, the gain is worth the time. The model is not in a hurry, and neither are those who tend to it. Imagine now a paleoclimate run. The model is given a world where continents are arranged differently, or where greenhouse gases are at levels known only from ice cores and sediments. The grid draws over this different world, and the model begins to step forward. The climate settles into patterns gently, perhaps warmer seas, perhaps different wind patterns, perhaps monsoons that shift in timing. The run takes a long time because the deep ocean must find its rhythm with the new arrangement. The patience required is itself an act of respect, a recognition that the planet's memory is deep. The gentle rhythm continues. In another room, there is a simpler model, one with fewer moving parts, used to explore ideas before asking the full climate model to confirm them. This model can be run many times in short order, building intuition about sensitivities. It is like sketching lightly before committing to paint. When the sketch matches the quiet logic of known outcomes, and when it suggests something slightly new, the full model is set to work with that idea in mind. This layering of approaches creates a cushion of understanding that supports the slower runs. Inevitably, there is uncertainty, but in this context, uncertainty is not a void. It is a measured range with a shape. That shape is described gently in terms of distributions. One outcome is most likely, another less likely, and the tails far out are noted as possibilities to be considered carefully. The climate model helps chart these shapes, and by doing so helps people chart their plans. Uncertainty becomes something navigable. The gentle rhythm continues. There is also a simple numerical truth that contributes to the long duration of climate runs. The cost of computation grows with the cube of resolution in 3 dimensions, and with the additional factor of smaller time steps. This reality carries a certain serenity because it is transparent and unavoidable. It informs choices. It guides the design of experiments. Deep down, it reminds everyone involved that patience is built into the craft. As your breathing deepens, imagine again the sum of it. The grid cells passing whispers along their edges, the multiple subsystems exchanging notes, the balances checked and rechecked, the saving of states, the writing of outputs, the careful coordination across machines and among people. It all forms a steady pulse against a background of silence. It is easy shows a gentle gradient. A chart of precipitation reveals shifts that are meaningful but not jarring. Working with these, scientists construct summaries that are useful for planning. Then the model resumes, moving on to the next month, the next year. The gentle rhythm continues. Sometimes discrete improvements arrive that shorten the wall clock time without changing the essence of the simulation. A communication routine is made more efficient so that data pass between machines a little more smoothly. A solver is replaced with one that converges in fewer steps. These are like smoothing a quilt so that it drapes more naturally over a bed. The comfort increases, but the fabric remains the same. The gentle rhythm continues. In places, researchers use nesting techniques, where a finer grid is placed inside a portion of the globe to study a region with more detail. The outer coarse grid provides boundary conditions to the inner fine grid, and the inner grid, in turn, informs the outer. This nesting brings the subtleties of coastlines and complex terrain into focus for regional studies, while keeping the global run manageable. Even so, the approach adds complexity, and the time steps in the nested region must be small, so the overall run remains deliberate. At today's edge of capability, some projects resolve individual storms across the entire globe. These convection-permitting models, at kilometer-scale resolution, have an intimacy with cloud structures that is mesmerizing. They also demand tremendous computational time. To run a simulation for even a few months is an undertaking. Those who do this work are aware that each minute of model time is precious, that the data must be handled with care, and that the insights gained will help all models in the long run. The gentle rhythm continues. Meanwhile, routine climate projections, the ones that inform reports and conversations around the world, proceed at resolutions that allow whole families of runs to be completed without losing decades to computation. This balance is practical and wise. You would not try to count grains of sand when what you need is a sense of the shoreline. The climate model counts what matters for climate and leaves the fine texture to specialized studies. In the final stretch of our quiet review, it is comforting to remember that the aim of these models is not to catch the exact weather on a given Tuesday in a distant year. The aim is to describe the field of Tuesdays, the gentle spread of possibilities for seasons, the slow leaning of the averages in response to changes. In that sense, the model's slow pace is in harmony with the slow pace of climate itself. The ocean does not hurry. Ice sheets do not hurry. The balance of energy does not hurry. The model listens. And so we arrive back at our first image. The Earth wrapped in a grid like a quilt. Each cell a careful observer. Each time, step a calm heartbeat. The model steps forward, pauses to rebalance, steps forward again. Light enters, air rises and falls, water circulates, plants breathe, ice flexes. The main character is patience. The plot is persistence. The theme is balance. Imagine yourself now floating above that quilt, comfortable and weightless, held by the gentle hum of understanding. relationships unfold in their own time. This is the quiet work of grids, a work that can lull us not to forgetfulness, but to a peaceful trust that careful attention exists in the world and will continue. As you return from this slow journey to the soft